Okay, let's dive in. We all interact with JavaScript constantly, right? It powers, well, pretty much everything dynamic on the web.
Absolutely. From complex apps to simple animations.
But here's the thing that always gets me. JS is single-threaded. It does one thing at a time, synchronously, line by line.
That's right. The core engine is built around that synchronous execution model.
So, how does that work then? If I click a button that needs to fetch data, say something that takes 5 whole seconds, shouldn't my entire browser window just freeze, lock up completely?
That's the paradox.
Yeah.
It would freeze if JavaScript itself handled that waiting. But it doesn't.
Okay, so what does happen?
It cleverly offloads those long-running tasks. Think of things like set timeout or network requests using fetch or even listening for clicks. These aren't handled directly by the main JS thread.
They get pushed off somewhere else.
Exactly. They're handed over to the browser's web APIs or the Node.js environment if you're server-side. These are like external departments that can handle timers or talk to the network.
And the main JavaScript engine, the call stack, just keeps chugging along with its synchronous code.
Precisely. The call stack's rule is simple. Execute the current task,
Yep.
finish it completely, then maybe take the next one. It has to be empty before anything new can come in from the outside world.
Okay, so the web API finishes its 5-second data fetch. It has the data, and it has the callback function, the code that should run after the fetch is done. Where does that function go? It can't just jump onto the call stack, right?
Correct. The call stack might be busy. So the completed callback waits. And this is where things get interesting because there isn't just one waiting room. There are two.
Two queues.
Yep. First, you've got the standard task queue, sometimes called the callback queue. This is the general waiting area.
For what kind of things?
Think set timeout callbacks, even with zero delay, or callbacks from user interactions like clicking a button, those DOM events. Pretty much the classic asynchronous stuff.
Okay, the general waiting room. What's the second one?
The second one is the microtask queue. You can think of this as the express lane, the high priority line.
High priority. What gets VIP access?
Primarily callbacks associated with promises. So when a promise resolves or rejects, the code inside .catch or .finally gets queued here. Also, things explicitly added with queue microtask.
Promises go to the microtask queue. Set timeout goes to the task queue. Why the separation? Why does this priority matter so much?
This is the crucial bit. It's all about responsiveness and predictable state updates. Imagine you fetch data, a promise, and immediately want to update the UI based on that data, the done callback. You want that update to happen right away as soon as the main thread is free.
Before some random set timeout you set earlier gets a chance to run?
Exactly. You don't want a less critical timer, potentially delaying an important UI render that depends on freshly fetched data. The microtask queue ensures that promise-related follow-up actions happen almost immediately after the current synchronous code finishes.
So let me walk through this. Synchronous code runs on the call stack first, then the stack is empty, the event loop looks around. What does it check first?
It always checks the microtask queue first. And here's the key rule. It will run every single microtask in that queue, one after another, until the microtask queue is completely empty.
It clears the entire microtask queue before even thinking about the other queue.
That's the rule. Only when the microtask queue is empty will the event loop take one single task from the task queue, move it to the call stack, and run it.
Wow, okay. One task from the task queue, then it checks microtasks again.
Yes, after that single task finishes and the call stack is empty again, the loop repeats. Check microtasks first, run them all, then check tasks for one more.
Let's solidify this with that classic example. So we have this code, .console.log, canafault, then set timeout, console.log 0 dinner, then promise.resolve.log, and finally console.logd. What's the output order?
Okay, step by step. First, the synchronous stuff runs on the call stack.
So console.log A runs, output A.
Then we hit the set timeout. The browser's timer API takes the B callback, and the 0 means delay. It will place B in the task queue almost immediately, but after the current script finishes.
Got it. Next is the promise. It resolves instantly.
Right. And the then callback, C, gets put straight into the high priority microtask queue.
And then the last line, console.log D, also synchronous.
Runs immediately on the call stack. Output now, A, D. And with that, the main script is done. The call stack is empty.
Okay, stack's empty. Event loop's turn. What does it see? It sees B in the task queue and C in the microtask queue.
And what's the priority rule?
Microtasks first. Always empty the microtask queue. So C is pulled onto the call stack and runs output, ADC.
Perfect. The microtask queue is now empty.
Now the event loop can finally check the task queue. It sees B.
It pulls B onto the call stack, runs it. Final output, ADCB.
ADCB. The set timeout with 0 delay ran last, even after the promise callback, because of that queue priority.
Exactly. That 0 milliseconds isn't a guarantee of immediate execution. It's a guarantee of minimum delay. It runs only after the stack is clear and the microtask queue is clear.
So the big takeaway here is synchronous code first, always. Then all microtasks, like promise callbacks. Only then do tasks like set timeout or click handlers get a look in, one at a time.
That's the core mechanism. And understanding this is fundamental to really getting why promises and async await, which is built on top of them, are so powerful and efficient for handling asynchronous operations in modern JavaScript. They leverage that microtask priority.
Right. It gives you finer control over the exact order of operations, especially when things depend on each other. Which leads to a final thought for you listening. If this microtask priority ensures certain actions happen before others, what specific real-world UI problems does this solve? Think about situations with multiple fast data updates or user interactions happening close together. How does this prevent visual glitches or ensure data consistency on the screen? Something to ponder.